Okay, guys, I'm ready to go. Sorry. Yeah, I failed to share, failed to deal with Zoom today, and I will start yelling louder. Okay, let's get to class. Yes, okay. So people on Zoom, am I recording and sharing, right? So you can see my screen and everything. I assume so because something didn't work for me from the first time. Okay, let's get back. Yeah, go ahead. Question.
Yeah, quick question. When submitting our homework, how do you want to show our work? Do we just like type it in as best we can to the grade submission, or is there a way to like actually upload the?
I think that okay. So the question is like how to show your work. So yeah, that's a great example. That's a great question. So I would say whatever is easier for you. I'm pretty sure that you can submit like a photo of your work as well. I didn't try myself. I can quickly create a student account for myself and try. So does anyone know if you can like submit a PNG file or something when you?
I couldn't find the way to do that.
Oh, you were not able to find? Okay, let me. let me take a look at it. So I guess for us it's easier if you just type, but if it's yeah, I understand there is a not everything is easily typable on Gradescope specifically. Let me you mean like formulas and stuff, but it supports Markdown, but I don't recommend like playing too much with it, I guess. Let me play myself. I'll create an account for myself, try to submit my work. But in general, the high level point here is that you actually have to show your work. So if you just put a number, we'll probably will not count it. And the way we structure the rubric, right? So even if you make a mistake, it's okay, but you will lose just a couple of points. But if you show logically your work, we will subtract only so little for the fact that you missed the calculation or something like that, right? Any other questions about the homework? Actually, so I moved it to Friday night just because I accidentally typed Friday night on one of the whatever Canvas or website. I forgot, and of course didn't move the deadline forward. What else? There will be a homework this week as well. So, but you kind of got the flavor of it, right? So I assigned several questions from the book essentially. I mean, I was thinking of coming up with something myself, but like book is reasonable, and I actually skipped the hardest, right? So everything what I assigned was aimed to help you to learn, not to kind of.
What the fuck?
So it's reasonably, I mean, it's not hard, and that's how it will go in the future. So in my first, when I was doing the introduction lecture, I was thinking, okay, we're gonna do something hands-on on with Bash and C programming on real servers. So that's probably is going away. So because I underestimated your level of, I was thinking you'd like proficient with Bash programming and stuff.
We have the PowerPoint.
So someone on Zoom, can you mute yourself? I guess we can hear someone. But instead we're gonna be using a MIPS simulator, right? So it's coming probably next week. And it's like, will require you to type real MIPS assembly, and it has to actually run on that machine, which and it's a machine which we're covering in class. It's a lot of fun because it's real, so it emulates faithfully the hardware, right? So you will have to type assembly instructions. But one more homework will be just theoretical on paper, meaning theoretical, like type some assembly instructions, do something like that. Right. Okay, good. Anything else about the homework? My office hours actually are today, right? So at 1:30, and I actually moved to a different temporary office, and I will post it on Canvas real quick. I forgot the number. I don't remember. Good. Okay. So, okay, so this is where we were last time, and today our goal is to cover more MIPS and essentially get conditional branches, see how the if then else statements and loops are compiled to MIPS assembly, and get to procedures, which we will cover early next week, right? So last time what we were doing is we were saying, okay, we understand that every number is a 32-bit value on this machine, right? And we know how to represent positive and negative numbers. Essentially, here is the example which asks you to convert 5. And remember the formula, it's like 2 to the power 0 multiplied by this 1 plus 2 to the power 1 multiplied by 0 because we have 0 here, and 2 to the power 2 multiplied by 1, and everything else, and so on to do the power.
Hey, Professor, we can't see your screen on Zoom.
Oh, you can't see my screen, but I can hear you. Cool. That's yeah. Being able to enable live transcript. So why can't you see my screen? So Zoom is that's what I was dealing with in the beginning. Yuck. My life is never too good with Zoom. Return to meeting. No. Anyone has suggestions for how to deal with this? Yeah. Chick. Why would Zoom do that to me? Return to meeting. You see the window somewhere over here. Okay. Open Zoom. Already on Zoom. Return to meeting. settings. How do we get there? Yeah. Okay, let's do it again. Okay, hopefully that will work. You can see it now, right? And what I was trying to show here real quick is the following. And okay, so we got the conversion, right? So this we understand how to convert. And the negative numbers, the formula is slightly more involved, and you can look it up in the book. But the idea is that if for the positive numbers, we cover everything from 0 and go up to the max number, which is like all ones, right? Which is 2 to the power 32 minus 1, just because we shifted to left to cover 0, right? For the negative numbers, we will cover like half, essentially. Hold on, like if I want to draw up to scale, so it will be half of this range, right? Here and here. So this will be covered. And the easy way to convert is essentially, it was called a 2's complement, right? So the formula was negate all digits of the number and plus 1. So just because it so happened that this is true, right? So essentially x plus x complement equals -1, right? Always, no matter what, because if you add two numbers, it will always add to a number to its own complement. You will always add with the number which has all ones in all positions, right? Okay, so I wanted just to remind that this is where we were last time. Sorry, and this is what I wanted to quickly recap. So right now, like typically when you work with computers, you deal with three number systems. So a decimal, binary, and a hexadecimal, right? So binary, I mean, decimal, we know that it's just hard to represent numbers because everything is a signal low and high, right? So that's why everything is stored as a binary number on the machine. When we will be building storage elements like actual memory or registers, right? You will see that you can either store 0 or 1, right? And that's why all the computations will be done on binary numbers. But for humans, it's a little bit too hard to deal with binary because the numbers tend to be large, long, right? So it's inconvenient, so it's hard to read. And so people usually deal with the hexadecimal system because it's convenient, because 4 digits in binary convert to 1 hex digit, right? So essentially it's easy, like if you can split a number in portions of 4, right, a long number, like for example 32, you can split it into start drawing here, maybe not successfully. So this will be like 8 bits, that will be 8 bits, this will be 8 bits, and I'll draw another one, you'll have 8 bits, right? And no matter, and then you convert them like to, if you say, for example, this is a binary 1000, so it's hex 8, so you can just write 8 here. If you, for example, here have a binary something 0101, so you know that it's hex 5, right? So because and the number in hex go from 0 to F. The last several are letters A, B, C, D, E, F, right? So you probably have seen it before. I just wanted to make sure that it's clear for everyone, right? So, and sometimes it's inconvenient because if the number is something like cannot be easily split into 8, 8, 8, and 8, right? So like, for example, we'll see later today, opcodes of instructions, maybe there are like only 5 digits, right? So that at this point it gets inconvenient, right? So we got three number systems. All good. Okay, So let's get back to the MIPS assembly, right? So this is where, again, this is where we were left. So imagine we have an example in which we need to add 4 to register as 3, right? So one way to do that, and this is how we've seen it before, is to essentially, the question is like, where does this constant come from? So what do you think? So where can it be? The constant number 4. We need to somehow bring it into our registers, I guess, right? So where will it be? A couple of options. Everyone is asleep because MIPS is like we had a long weekend, so it's hard to come back. Yeah, go ahead.
Part of the instruction.
Yeah, so like an elegant solution is to make it a part of the instruction, but unless you do that, you will end up with something like that. So imagine really like registers are in some undefined state. Let's assume that after the power on, they all are initialized with zeros, right? But it's not guaranteed, strictly speaking, right? And you say, look, where will be the constants? So the only way to store something on this machine is to put it in memory, right? And you say, look, everything what I want to be initialized to some specific value, I will put in memory, right? And here we say, look, we will have, the compiler will generate an address of the, address of this constant, right? And either put it in register, like in one of the registers, or we knew that we had this instruction. Like this is again from the book, but it's more clearly, remember there was this global segment GS register, which essentially holds the pointer to the program section, right? And this is some offset, and to be honest, this example is already contrived. So I would really prefer the book to write it as LW load word into T0 and use just some address as 0. The question again, it's kind of a loop here, right? A chicken and an egg problem. Like, what is the value of this as 0? And what the book was saying, okay, look, you can really put the address of the constant and then load it into the register, right? And then this 4 gets into T0, right here. And then if you want to add this to register S3, you use this add instruction, which takes as the old value of S3, adds T0, which holds 4 and puts it back into S3, right? And it's a little bit awkward. And that's why this instruction set provides an immediate an instruction which allows you to use an immediate value, right? So note this I here. So it's add immediate, right? So, and why is that so? Because those operations are quite constant. And again, to change your cycles per instructions and just number in even the number of instructions in the program, right? You try to generate denser code, and they say, okay, look, we'll add another instruction, not just addition, but the one which allows you to put a constant here, right? So essentially, if you want to do something like S3 plus 4, put it back into S3, that's the way how you go about it. And those instructions are called immediate instructions, which take a constant, right? Go ahead.
For those immediate instructions, do they do the process from above in the background for you? Or is it a different process that it goes back afterwards?
It's a different process. Let me get back to it in just a couple of slides. And the reason I was kind of talking about it is that I wanted to introduce you to an actual encoding of those instructions, right? So remember, we already agreed that all instructions are 32-bit words in memory, right? And up until now, I was using something human readable, right? Something like add T0, T1, T2, and I'm like, I don't want to put $signs, but I should here just to make it a little bit cleaner, right? But the real encoding is actually this. So the whole thing here is 32 bits if you add all this 6 plus 5 plus 5. And this is the format in which instruction is actually stored in memory, right? This is how the machine reads it. and execute it. And it has multiple fields. So the first field is operand, right? So it's a basic or operation, basic operation of the instruction, traditionally called the opcode, right? So it allows you to encode, it uses 6 bits, right? So it says, like, you have a limited number of instructions, right? So you don't have unlimited, you have addition, subtractions, and each of them gets a number, right? And so you can encode essentially 2 to the power 6 different instructions, right? Agree? However, there is an additional field here, function, which for each instruction, so maybe this encodes addition, and maybe this will change it to something like addition on a sign or unsigned number. So essentially, this additional field function, and we will see in a table specifically how it changes, selects the specific variant of the operation in the op field, right? So there is a operation and there is a variant, right? This function. And remember, since I usually write these 3 things here, so 2 are input operands to the instructions, and 1 is output, right? So here we have these 3 fields, RS, RT, and RD. Each of them is 5 bits, right? So which allows you to encode 2 to the power 5 or 32 different registers, right? And it's kind of nicely follows that this machine actually has 32 registers, and you can put any register. So it's a register source, the RT as the second register source, and RD is the register destination, right? So this one is this, RS is this one, RT is this one, right? So essentially, for each instruction, you put some operand, registers which are involved here. We don't cover shift amount right now, but when we get to the shift instruction, it will this field will be encoding the number of bits by which the register has to be shifted, right? And in a more specific function for this operand, right? And I'll give you a couple of examples, but this is how it's represented in memory, right? Any questions about it? So, okay, go ahead.
So when we're adding a constant, the constant has to be a 5-bit number.
That's a great question. So this is for R-type instructions, right? And this is specifically the observation which you're making is the limitation for which this R-type encoding does not work for operations which require an immediate operand. So, and we will see in a second another encoding for I-type. I stands for immediate here. So we'll have multiple encodings. I mean, I think there are like 3 of them. For jumps, R-types, and I-types. So I is immediate, right? So, but this encoding is convenient for encoding instructions which operate on 2 registers and put result in a 3rd register, right? It's kind of easy, right? So here's a couple of examples. Not an example, that's exactly this observation which you just made, right? So this encoding, R-type, works well for instructions which operate on 3 registers, right? But if you have an instruction, something like a load word or addition immediate, you say, look, I really have to figure out the space where to put this immediate constants, right? And moreover, you say, look, this only requires 2 registers as arguments, right? So really, this one will be somehow, let's say not this one actually. But this one is typically not needed. And you say, I'm really just wasting, I'm wasting 5 bits here. And you can say that maybe I can fit the immediate value here, but then as you say, your immediate constants will be limited to 2 to the power 32. 2 to the power 5, which is 32, which doesn't give you a lot of constant space, right? So this is kind of annoying. And so what they came up with is that for those instructions which are assuming an immediate value, the encoding is slightly different. The beginning of the instruction is the same. So it's the same operand operation here, same source register. This RT changes its meaning, so I would rather prefer here to be RD, but I mean, this is how they write it, RT. So, but say that destination register now. And here you have the whole 16 bits for the constant or immediate value. which allows you to encode 2 to the power, two to the power 16, right? So what is this number to the power 16? Who remembers? 64K. Am I right? Right? No. Here's my calculator here. Probably right. I'll use Python. And I will be multiplying 2 to the. And I don't know how to actually type it fast. 32 by 32. 1000. Power. Okay, like this. Yeah, and we have 16. So yeah, 64 kilobytes, or this exact number 65536. And if you choose this space, whether it's signed or unsigned numbers, so you will be able to represent either half of it from negative to positive, or from 0 to 65536, right? So okay, so now we have 2 different codings. One is for register R-type instructions, and one is for instructions which carry an immediate value, right? And it seems to be logical. Again, you can structure the hardware which looks at this op field and quickly realizes whether this instruction is an R-type or an I-type, and then does decoding differently based on this information, right? Okay, so here's a couple of examples. So our old add instruction, obviously it's an R-type instruction. This number is just essentially the op number is an agreement by, like, when you design the hardware, you choose which numbers you will assign to which instructions, right? And so you have 3 registers. Shift amount is 0 because it's not used in the add instruction. The function type is 32, and 10 here says that it's like, instead of using binary encoding just for simplicity, so it's easier for us to read, the table uses a decimal encoding here, right? And the address is not available, right? Because we don't do anything. An interesting bit here is the subtraction, right? Has the same op, and just the function changes from 32 to 34. As we will see later, the subtraction is a very similar operation. It's just like, we'll change just slightly the logic which implement addition to implement subtraction. We will invert the number and just do something with it. So it's like, it's a very simple, they are almost identical in terms of implementation, right? Immediate addition here is an I-type instruction, right? So it has a different opcode. So it has 8 here, uses only 2 registers, source and destination, and uses a constant here in that field which has 16 bits, right? So similar, the load and store instructions, they are encoded as I-type instructions. Load is has a operation is 35, store has 43. Again, 2 registers, one is a source, one is a destination, and in that field, which we use for which takes 16 bits, instead of a constant, immediate constant, we use an address, right? So essentially, remember that load something into register as 0. If you write something like 16 of as 1, what it means is that this address, the hardware essentially computes the value which is kept in S1 plus 16, right? Agree? So 2 encodings. Is it clear for now? But we'll see one more later on for jumps. Good? Reasonably simple. So again, and so people came up with specific conventions. So right now we mostly use those, a couple of those registers S from S0 to S7, which are in this canonical MIPS. They keep the values of variables, and temporary registers from T0 to T7. So S0 gets assigned numbers 16, S1 is 17, and so on up until 23, right? And again, it's just a convention. There is no super big magic behind it. So you can split this register space in a different manner, right? So for T0 gets assigned number 8, T1 gets assigned 17, right? So, and you can see that, okay, if we want to encode an instruction, so for example, something like this, we have an array in memory and we want to add H to the array element 300. So what do we compile this code to? It's actually almost identical to the homework, or somewhat identical, let me guess. So what is our first instruction here? We can make some assumptions about where those guys are located.
You would add the 300 to the base address of the variable like A, like to get the address of the variable that we want to get out of the.
So imagine this one is an address as is in register as 0, right?
Okay.
So then what you're saying is that you're saying 300 to register as 0, right? And what is here? Yeah, do you know? Hold on. So, okay, let's, for everyone, because it's close to the homework, like I'll come back to you in a second. Remember, imagine this is your memory. So at a high level, what do you have to do? Imagine this is this array. As 0 points to the beginning of the array. Each element, don't forget, like 4 bytes, right? And what you want to do is imagine this is element number 300. You want to take the value from here, take the value from here, load it in one temporary register, agree? Then add H to this temporary register and store it back. So roughly speaking, you can eyeball it and say, okay, I just need 3 instructions. Load, addition, and a store, right? Agree with this? Just because there is no instruction which adds immediately in memory in this instruction set. So I argue that this first instruction should be a load, right? Then this should be an add, and this should be a store, the last one, right? That's what you probably were saying, right? So, and I agree with you that instead of this 300, we should probably put 300 by 4, whatever it is, like, so whatever, 1200. Here we can pick a temporary register T0, for example, add a value in T0. Imagine this one is inside S1, for example, add S1 to T0 and store back into the same. So essentially we say T0, which contains our computation 1200, and again, like S0, right? I agree that that's a meaningful translation. Yes, no, I have it on the next slide, so you don't have to really copy it.
Just clarification, when we're like indexing into that array, do we write the number of bytes or the index value that we're trying to access? So we write 300 or 1200 if it was for actual code we were going to try.
Yeah, so the machine, that's a good question. So, and again, this example is a little bit underdefined because I'm not saying what this A is, right? And it can be anything. So I just for simplicity assume that it's a word. Each element of the array is a word, right? So, but it can be like maybe a double word and then something else is happening, right? So machine only understands addresses, right? So you always put an address here. So it's a literate offset in memory, right?
So it'll be the number of bytes then. So
It will be a number of bytes. Yeah. And if it's a different type, so maybe it's a byte or maybe it's something else, then the translation will be slightly different, right? And you would use the actual address of this array in memory, right? So yeah.
Why is it 1200 instead of
because I assume here that this is an array of, for example, integers, right? So each integer is 32 bits or 4 bytes, right? So, and this is actually what we have to put here is not the offset within the array, because machine doesn't know anything about types. It just knows about addresses, right? And you have to put the exact address, right? I agree.
How do you multiply by 4?
how would we multiply by 4 if it's a variable, if it's a dynamic index or something like that? The compiler, there will be a multiply instruction, and then you would do this on register. So you would, your index, this 300 would be, for example, I in your program, right? And it would be an index would be in register, and you would multiply this with a mul instruction. Or I argue if it's a multiples of 4, it would be just a simple shift, right? Because multiplication by 4 is a shift by 2. I don't know if you're familiar with this trick, but you agree that that's how it will be. Yeah, go ahead.
Okay, so I'm going to say that the reason that you load the word for the time 4 because each section contains
4 bytes.
4 bytes.
Right. Exactly. So because this is how we represent integers, because we want them to be 2 to the power 32, right? Good. So let's double check. So this is from the book, right? But essentially it does exactly what we've done. Modular maybe that they assume that the address of the array is inside the register T1, and they assume that H is inside S2, right? So good. Any other questions about this example?
What if the object is on this is a variable instead?
Right. So this was the question from your classmate just a second ago, but let's do it again. So imagine you have I here, right? And I assume that I, for example, is I is inside some register. Let's assume it's inside T1, right? Okay, T1 is already taken. Let's assume T2. What I do what I will do is there, I would probably assume that you can say, let's compute the index for this operation, for this load, and write something like imagine this is a literate index. So what we have to do is index to, let me just clear it, sorry. So what we want to do is convert from index to adder. So it's index multiplied by 4, right? And then you use this adder inside this load instruction. So I can, if I put the adder in something like, inside something like T2 register, then I can write something like 0 of T2 here, right? Agree? I lost that person. That was you, right? So agree with the statement, right? So that will work because it's 0 plus T2. Now the question is like, how can we get T2, right? So T2, we can do something like either do multiply, which, for example, puts something into T2 and uses, for example, and multiply immediate. So for example, T1, which contains I, multiply by 4, right? And then that's how we convert to the index. I argue, and I didn't cover yet multiply instructions, that instead of this multiply, we can use shift logical left and essentially just do T2, T1, and the shift amount is 2. By shifting by 2 is multiplying by 4, right? Shifting by 1 is multiplying by 2. Shifting by 2 is multiplying by 4. Agree with that? Okay, this is clear. So one more question. Yeah.
What is the add argument there?
What is what?
You don't add the article I times 4, and I'm unsure what that has to do with it.
Oh, can you speak up a little? I'm sorry, I cannot hear.
Oh, I was wondering what does the ATR mean, because I have no idea what exactly this has to do with it, like something in MIPS.
No. Okay, let me explain. So imagine again, this is your memory, right? You as a programmer, you say, I keep an array in this memory, right? And I will be saying that I is my index into this array. So element 0 is the first element of the array. Element 1 is the second element of the array, right? But however, it's somewhere in memory, which goes, for example, from 0 to some max address, right? And if you say that you have an index into the array, right? In order to convert from an index to an address or an offset within the array, right? You have to multiply it by 4 because each element is 4 bytes. agree with this? Is it clear? Go ahead.
Why is the zero, isn't the address really just the offset?
Right. No, I was thinking about the same just a second ago. Yeah. Okay. If you want to be concrete, and that's good, because if you really write a MIPS code, you would do something like, imagine this is your this is all of your memory, and this might be, you know, S3 contains the beginning of your array. I, which is in T1, is here, right? So really your address here is plus S3, right? And then you have to incorporate it into your equation. So essentially you have to add yet another instruction which converts between the, if this is the base address of the array here, this is the index T1, and each element is 4, right? So you really have to use an index as an offset, right?
Is using the shift left logic a more cost efficient way?
Right. Right, exactly. Because the question is like, why is that I switched from multiply to a shift left? Because multiply typically takes around 4 cycles, between 4 to a little bit more cycles. But shift executes in 1 instruction. So that's why you will see a lot of those optimizations when you have divisions and multiplications. Multiplication is still reasonably fast. Division is really expensive. So essentially division or like modulo operations, which are not power of 2, are kind of costly. You will see real impact when you build something like hash tables and stuff like that. And so it's all good when you say, you know, when you say that my hash table is a power of 2. It starts playing against you because sometimes it's like a gigabyte, and I'm like, what, gigabyte and a half suddenly takes you 2 gigabytes, and you say, okay, it's too much. Then you have to do something else. Well, we can come back, but you will see, and it's again, this is, remember we talked about the compiler and the language, and compilers typically can, if the hash table is defined with a specific constant, there's optimization which is called constant propagation, which allows the compiler to reason about that constant and actually substitute all the multiplications with shifts, divisions with shifts as well, right? But sometimes compilers are confused, and you will suddenly see, okay, it's a power of 2, but my hash table is insanely slow. And then you look at the assembly and you see a division. That happens in practice sometimes. Like, and you slightly change the code, just literally just add a line or 2, or like put it inside a function. So it sometimes happens. Any other questions? There was a question.
Why do we assume that variable h is in this too? But is it like to tell that it's after the array or before the array?
No, I just blindly randomly assume. There is no logic in that. I just follow the convention that variables is in those S registers from S0 to S7, and temporary values in T1, T0 to T7. But really just, I just pick a random number. There is no, compiler will not care. And I'm pretty sure that like compilers will abuse, the distinction between S and T will be very, very minimal.
Those don't conflict into the array at all, right? In memory.
Say again?
Those don't like conflict in memory.
Okay.
Like the array is
Hold on. So this is again, this is maybe that's a good question. So just looking for space, right? So maybe I misunderstand what you're asking, but I wanted to come back and make sure that it's clear for everyone. So this is memory, or I sometimes say DRAM, just because that's how we call it, like random access memory. And registers are sitting on the CPU, right? So internally, they're just like bits of CPU logic, right? So this is S0, this one is S1, and so on. This one is like T0, this one is T1, and so on, right? And later in class, we'll see how to build the register. The register is a memory, but a very fast and a very small one, right? It can be accessed within the same cycle, right? And it just, at this point, is just a logical conversion, logical, what I wanted to say, logical agreement on what T like S will hold. And if I say that S0 holds a like an address of H, right, which is somewhere here in memory. That's just my convention. Maybe S1 will hold the beginning of the array, which is here, right? This is my array A, and maybe T0 is an index, right, into this array. And maybe in some of my computations, I will convert between an index to an offset, and T1 is like, if this is an index, this is an actual offset, which points, like, index is your logical in your head, but this will be an actual offset, right? And then the address of this element, which I'm trying to access, will be something like S1 plus T1, because T1 is the offset, right? And how do we get T1? T1 is actually equals T0 multiplied by 4, something like that, right? So, but
The registers are just pointing to a location. They're not like pointing to a block, they're pointing to a start point. And that's why you use offset.
registers are just numbers.
Yeah.
They are just numbers from like we were saying, zeros and ones, right? Machine just interprets those values. If the register is passed as an argument to a load or store instruction, right? So whatever, if there is some offset here, but let's assume it's 0, and I put T1 here, right? Machine uses this value as an address, right? That's what machine does, and it doesn't do anything else. And it loads the value, which is here, which is in this dashed area, and puts it inside whatever, let's say T2, for example, right? That's what machine is doing. Machine always treats it as an address. And if you put something, if there is an immediate value here, because we have, remember, we now know that we have 16 bits for immediate value, so we can put something like, I don't know, 324 here for whatever reason, then it will be, the address will be interpreted as T1 plus 324, and you will end up somewhere over here, for example, right? So is that clear now? Like, really, everything is relatively simple. So it's kind of like a very verbatim system. It doesn't do anything. It doesn't try to reinvent anything underneath or guess anything.
So if you just put a random number in there, just change some random value to some random location.
Yeah, exactly.
Cool.
Yeah, no, but you've seen it in your real life, right? So you accidentally don't check for the bounds of the array, and you get a segfault. Sometimes this segfault shows up 2 hours later because you overrode some other data structure which is not involved in that computation, and only later when you try to press a button on your GUI interface, the button just collapses, everything just crashes at that point, right? So sometimes it's very spectacular to see those crashes. And that's why, I mean, a good practice, and I don't know if you know those words, and sorry again, I go off topic, address sanitization, right? So if you use an unsafe language like C++, the address sanitizer will try to catch those crashes sooner by essentially inserting specific values and write protecting memory to make sure that you crash sooner than later. Probabilistically, it works. Okay, good. So this example is clear, right? So this is close to the homework, right? So now we understand how it works. And again, it's relatively simple, I kind of argue, right? So if you just imagine you're this machine, and just say, I'm not going to do anything, not going to guess about what the size of A is. It's just verbatim execute those instructions. Okay, and this is what will the assembler, right? So if you write this in a human readable assembly, so if you write this in C or C++, this is typically done by a compiler, like this conversion, right, from C or C++ to an assembly code, and this conversion is done by the assembler, right? And this what assembler will generate in memory. So for example, this load, remember, we had this table here, load is 35 here, right? So this is what we specifically put in this op field. So 35 RS, what is it, T0, hold on, yeah, it's T1. T1 is 9, T0 is 8, 1200 is here in this field. Addition, remember, it's a 0 operand, and a function is 32. What is it? Register S2 is apparently 18. T0 is 8. Destination is T0 itself, 8 again. Address or shift amount is not used by add, so the agreement is to put 0 there. And finally, the store instruction is opcode is 43. T1 is 9. T0 is 8. And again, the immediate value is 1200, right? So that will be, if you take the hex editor or whatever, any editor, open the program, you will see those numbers there in binary format. So if you convert this one into binary, you'll specifically find the instruction there, right? This is clear. Okay, reasonably simple. And again, like just coming back to this table, we already seen it before. So the main observation here is that there are R-type instructions and I-type instruction, and I allows you to put a 16-bit constant which is used by those instructions, either as an offset in the array in memory addressing instruction or instructions, or as a constant. So you can also make an observation that it's actually not so trivial to switch from 32 registers to 64, right? So if you want to make the switch, what needs to happen to those instructions? No, why is it not trivial? Okay, go ahead.
Well, because you need to add like a whole other 32 bits to each instruction, and like also probably the register size and everything that will
the register size will change, but it does not reflect on the instruction set. But what you need is now if you use 5 bits, right? If all of them are ones, that just encodes 31, right? And you need an extra bit to encode numbers from 0 to 63, right? So you say, hold on, I need a bit here, and a bit here, right? So those bits will have to come from somewhere. And you can play tricks. You can say, okay, forget about this nonsensical shift amount, right? So for the shift, we'll come up with some other encoding, right? And then you'll have enough bits, or maybe you can sacrifice some of those function bits, because maybe you say, look, my instruction set is so tiny that it fits. You don't really need how many bits, 6, I guess, here for this function, right? But you have to play, like, your instruction encoding will change, and you have to be careful about what's happening, right? So with loads, of course, it will be a little bit trickier here, because again, if you take 2 bits, then your address, you will either have to sacrifice your address space by subtracting 2 bits, or kind of dividing it by 4 instead of like 64K values, you will be able to encode only 16K values, right? Or maybe you can do some other trick, but which will be less elegant, I guess. But that's you need to understand that, okay, if something like that happens, the instruction set has to be changed. Or you can go radical and say, okay, my instructions now are not 32-bit words in memory, are instead everything is 64 bits in memory, right? Then you have a ton of space, but what's the disadvantage? Now you have to fetch, your programs are twice as large in memory, right? So if you really program for very, very tiny devices, like imagine, I don't know, some temperature sensors that will increase the cost, sorry. Or if you like in the upscale machines, then you have to redesign memory buses and stuff to make sure that you can fetch twice as many bits from memory bus, right? So it's those changes, they will hurt you a little, right? So, and again, so if you substitute all of this with binary, that's the actual thing which will be sitting there in memory, right? So now we kind of understand this is like the whole pipeline from the C language to assembly to an actual machine encoding, right? And we only know a subset of MIPS, right, which is very tiny, but we'll learn quickly, we'll learn more, right? Yet another table from the book, we can probably skip it. Okay, so let's move on. So let's take a look at more operations, essentially. Right now, we were concentrated on just 4, right? So addition, subtraction, load, and store, right? So you need to do something on like bit operations are useful, right? Because you often end up doing something with them, right? So this machine offers several. So there is a shift left logical, shift right, and in C this is the sign. In Java it's the same. Shift right as this one, shift right logical, bit by bit AND. So it's AND 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 immediate version, because you can AND with a constant. You can do a bit OR, so again just on registers or with an immediate constant, and you can do a NOT, right? So which is a complement here, which is NOR instruction in MIPS, right? So, and finally, when we start talking about shift, just to give you an example how shift works. So if this is your number, everything is zeros, so which is number 9. And if you shift it by 4, you just add 4 zeros here, right? And it turns into 144. So which is essentially, if you divide 144, so you shift it by what? By you multiply by 16, I believe, right? And remember this encoding. So up until now, in those R-type instruction, this field was never used before, right? It was always 0 for addition subtractions, right? So for the shift, this is exactly where this value goes. So shift amount is this value which goes into that field. Which again raises the question, by how much you can shift. Tell me. It's okay. You don't really need a big number here, because the entire word is only 32 bits. So your max shift is what? Shift by 31, right? So you only have to encode numbers from 0 to 31, or the size of this field should be only 5 bits, right? And I guess this is exactly why they picked 5. Right? Agree with this? Okay, so and now, like, finally, a little bit of fun. So up until now, we only know how to write programs which don't loop and don't branch, right? And obviously, you can't really write too much with this, right? Because there will be conditional branches. So MIPS provides you with 2 flavors of branch instructions, conditional and non-conditional. So for example, 2 conditional branch instructions are branch when equal. So essentially, it takes 2 registers as an argument, and it takes a label. Label is an address. So this is essentially an address. And what it will do is that it will go to this, it will change execution, jump to that address, right? If register 1 equals to register 2, right? So remember, typically there is a program counter which points to some location in memory, right? From where the machine fetches the next instruction. So since each instruction has 4 bytes, typically when you execute addition or subtraction or load or store, the next value will be PC plus 4, right? And that's how you go forward. That's how your fetch, decode, execute loop runs, right? But if you encounter in a branch when equal instruction, this PC will change and will go to this label L1, right? And these labels are generated by the compiler, because compiler knows, or by the assembler, because either assembler or compiler knows where the specific code will be in memory, right? And this is like, we'll see in a second. We'll take a look at the example. So the second instruction is branch when not equal, BNE. Same idea, register 1. If it's not equal to register 2, it will jump to L1, right? And the final version is just J and a label. It's a non-conditional jump. It always jumps. And you will see in a second why you need this non-conditional jump. Right? Okay, any questions about this 3? Okay, let's take a look at the examples. This is where the fun starts, right? So imagine we have this if then else statement in C. So it says if I equals to J, then execute this statement. F equals J, G plus H. Else F equals G minus H, right? Assume that F, G, H, I and JR in those registers has 0, S1, and so on, right? So what kind of code we need to generate? All right, yes, let's assume that this contains already F.
We have like one branch on the
Branch equals. So I is inside, what is that, S2, S3, S4. So you're saying S3, S4 to branch where? Where would you like to branch? Yeah, that's a valid encoding. Probably, I mean, I'm not saying that you're wrong. It's just that like both of them are kind of, they exist. So you say branch not equal, right? And you say S3 and S4, and you will branch where? To the then branch, since it's not equal, right? Agree? Oh, else, sorry, Myron, yeah, to the else. You're right. Okay, and labels are human readable. As I said, in practice, those will be just addresses in the end. Just, but for if you write in assembly, you can use human readable names for labels, right? And then assembler will translate them to actual addresses, right? So okay, so else we can mark somewhere over here and say this is the else. We'll write it like that with a column here, right? So what will be, so if not equal, we jump to else and we do this computation, which is what? Which is subtract, like what is that? S0, S1, so subtract S0, S1 and put it into F. Hold on. G is S1, sorry. Let me show you my trick for erasing. You haven't seen it probably yet. Ta-da. As good as erase. So we are subtracting S1 and S2, agree, and putting result in S0, right? Good. Now, slightly more interesting what we're going to put here. So the then statement is addition, right? Addition of, again, S0, S1, S2. The question is like, what comes here? Correct. So here, since we don't want to execute this instruction, right? So we have to jump over it. So you put J here and you put, I don't know, let's say do end, right? And your end will be here. And whatever comes after this, if then else, we don't really care, right? But that's the encoding. That's one possible way to do that, right? So and it's as good as many other ways. And this is what I was trying to show you earlier, but at least now you understand in details why it works this way, right? Okay, let me just jump here. Say again? Not equal, right? So if they're equal, we execute the then part, right? If they're not equal, we jump here. Say again? Yeah, so if they are not equal, let me just pick a different color. If they are not equal, we jump to else and execute this subtraction, right? And that's what we want. And then reach the next instruction here. Why is what?
why do you actually show if the answer correct? If they're not equal, so.
No, maybe I missed.
Oh.
No, maybe like I can encode this if then else with a not equal as well, but then you have to invert slightly more, right? So this encoding is slightly more concise. You got it? Okay. Okay, so this is we arrived to the same thing which was there in the book. So you got this point. Okay, what about loops? Imagine we have a loop. So we have a loop and say, what is this? So you're looking for k, right? So this is the loop which searches through the array and looks for k, right? So finds the index in the array in where k is stored, right? They agree? So I don't know, like again, I copied it from the book without thinking too much, but as an example, it looks a little bit odd, I would say. Say again? Sure hope. Otherwise, you go and overwrite your data structure somewhere, or you will go forever. It can happen. You're right. Yeah, this is funny. There is no exit condition. So never write this code in practice. Otherwise, you know, never write it on a Google interview. No, like if you for real want to write something like that, I mean, I wouldn't write it this way, but you at least have to add the exit condition saying that if you reach the end of the array.
Only looking while this index equals a. So if you're looking for the first number that is not.
Oh, it is looking for.
Oh yeah.
As soon as it's not equal, it's just gonna exit the while.
Okay, I agree with you. So let's assume it keeps looping until it finds something what is not k, right? Okay, better, but still, you can loop far past safe if suddenly all of them are k, right? But anyway, so what will we write? What will assembler write?
We want to start with like a label like loop. That way we can always jump back to it in the while.
Correct. That's a good idea. So IR is S3. This one is S5. So somewhere here we have to increment, obviously. So we will do add on S3, right? And so hold on. Where is my here? And I can do an immediate add, right? Because why not, right? So somewhere in the middle. But what will be our condition here? So you're saying branch not equal. Imagine we use.
Last time we did branch not equal was when we were done.
Yeah, so imagine we have some value which is here in temporary variable t0, for example, and you compare it with k, which is inside S5, right? So if it's not equal, you go to something like end, right? And we will put end somewhere over here, right? And so we just have to write a little bit for loading something into this t0, right? And we can again just imagine that what is our S3 contains I. So yeah, we can play whatever here, but let's just leave this load a little bit open. But we know how to deal with load in the arrays. Essentially, we can either, let's take a look how book solves it. So what they do is here's that like remember the array elements, which are four bytes each. So they use a shift to convert between index. So this contains an index I, right? So this will be an offset. Oh, sorry. And so if S if S6 is the beginning of the array, I would assume, right? Then this will be actual, after we add the offset to the S6, we'll get the address, right? So the actual element of the array over here, right? Then we load it with this 0 offset into a temporary variable T0. And as you were saying, branch not equal T0 S5. S5 contains K, right? My add immediate on the index, and it either jumps to the exit or non-conditionally jumps back to the loop. Go ahead. Not by what?
Why would it shift to the left by 2 bits?
Not 1? Shift by 1 multiplies by 2. Because it's a power of 2, right? So you have to multiply by 4. So is this conversion? I mean, what we did, what we haven't done here is that we forgot to add J to the loop here, which is kind of critical. And I skipped those steps, which are essentially resolved between the index to the array. And this actually, again, this is very similar to what we were doing in the beginning of the lecture when I was converting between the array A300, right? And you asked me, what if this 300 is in the register? So this is exactly an example where instead of 300, we're using I here, right? Okay, so any questions about the loop encoding? And you can actually do multiple encodings, so there is not like one. Say again?
Overlays?
Why?
Like loops and labels?
Loop is a label.
Yeah, like where's the label stored?
Okay, that's a great question. So where is the label stored? So where is it? Who can guess? Okay, I asked the question number 1. What is a label? It's a number which means what? Memory address. It can be a memory address to which the program counter will be changed. And we haven't talked about the encoding of the J. So you can imagine 2 different encodings. One is that when you say it's an actual address of memory, right, where you want to jump. But you can, if you start thinking on the exam that possible encoding for this J operation is probably some opcode here, right? And then you only have some subset of fields. So clearly you will not be able to cover the whole address space, right? Agree with this? So because op takes like 5 bits, for example, right? And you say like, oh, hold on, I cannot jump to the max address to the very end of memory. That's odd, right? So what you will have here is the relative value. So it's relative to the current PC. So PC plus label, I mean, it's not the label, but this offset which is kept here, that will be the encoding, right? But in the end, you're changing the program counter to a specific value in memory. Do you agree with this? And if you really, and again, you say, my argument, it kind of is still a little bit stretched. I can only jump relatively to so far. I cannot cover the entire address space, right? So there is a specific instruction which instead of J and a label takes J and a register. And I can put the address, 32-bit address in the register, for example, as 5 or whatever, and jump to the value, to the actual address, which is in that register, right? So are we clear now on what labels are? Or still unclear? I mean, I will come back next time with this encoding for the J instruction, right? But okay, so let's stop here and actually covered almost everything what I wanted. So thank you.
That's why it's been
Yeah, so we said that S6 was the address, but the manufacturer said that T1 was the address. So
No,
it's a
no,
little
look,
bit.
I'm just guessing. The address of the beginning of the P1 is the old and here we can work with the old set plus the base address, get the extra.
Yeah. I can put this on.
I was gonna go to your office hours.
Yeah, let's just give me like you can head over there. Let me quickly figure it out from just